What I want to do in this video is show you some NMR spectra for alkenes and illustrate the differences. So what we're seeing here is a trans isomer of 1,2-ditert-butyl ethene, or if you were to number it, carbon 1, 2, 3, 4, 5, 6. This is 2,2,5,5 tetramethyl 3-hexene, and it's the E isomer. We have 18 identical hydrogens right around 1 for the magnetically equivalent CH3 groups on each of the two T-butyls. We've got rotational symmetry around an axis here, so that the two hydrogens on the alkene are identical to each other and the two T-butyl groups are identical to each other. And then between 5 and 6 we've got a singlet, and since these are magnetically equivalent hydrogens, they're not splitting each other. And then we have our internal standard at 0. If we look at the difference between a cis and a trans isomer, and here what we're looking at is a propanoic acid. So in this case we're looking at Z 3-chloro-propanoic acid, and here we're looking at E 3-chloro-propenoic acid, because it's got an alkene as well as the carboxylic acid. The carboxylic acid function is down quite low, and it's very broad because it's an exchangeable hydrogen. In this case it's between 10 and 11, but it's often even further down towards 12 and 13. And when we have a cis isomer, we have a relatively small coupling constant between 6 and 10 Hertz. In this case it's a 9 Hertz coupling constant. Notice that these two hydrogens, since they're splitting each other, are leaning towards each other, and they're in the 6 to 7 range because of the influence of the carboxylic acid and the chlorine, in addition to the ordinary double bond, which would put them in the 5 to 6 range. We've got a very similar looking spectrum for the E isomer, but now the coupling constant is typically between 12 and 16 Hertz, so we're seeing a coupling constant of 14 Hertz. Right? Very, very similar, but the larger coupling constant tells us that this is the trans isomer versus the cis isomer. The carboxylic acid function is in about the same place either way, and the chemical shifts are not dramatically different, although this hydrogen is a little bit further downfield because it's greater proximity to the carbonyl group. One of the patterns you're going to need to learn to recognize that's very common in NMR spectroscopy is what we call an ABX pattern. Here they have the hydrogens labeled A, B, and C, but it's much more typical to label the two hydrogens that are attached to the same carbon as A and B, because they will have very similar chemical shift. And then this one, which will have a quite different chemical shift because of the proximity to the T-butyl group, would be the X. So their BCA would be my ABX pattern. So we've got a 9 hydrogen singlet, right? That's typical for a tertiary butyl group. And then downfield we've got 3 different resonances, because these 3 hydrogens are all magnetically different. HA is split by a fairly small, relatively speaking, coupling constant between hydrogen A and hydrogen C here. Right? That would be expected to be in the 6 to 10 Hertz range, and then a larger coupling constant between HA and HB here, which we'd expect to be somewhere in the 12 to 16 Hertz. So when you look at your splitting tree, this is upside down, you'll see that first the AB coupling, the large coupling, right, is splitting it by about 12 Hertz, or about 14 Hertz rather, which means it's going up 7 and down 7 Hertz. And then each of those signals is being split by hydrogen C by, say, let's assume it was the 7 Hertz coupling from before. Right? So we have coming up 7 Hertz and then going back down another 3.5. So we're separated by 7 Hertz here, maybe a little less than 7 Hertz there, and 7 Hertz there. That's a typical pattern, that doublet of doublets that you see, and it's downfield, right? Because the electron donating group, right, this T-butyl group is electron donating, increases the electron density in the pi system here, and an increase in the electron density in the pi system causes a downfield shift, because the local magnetic field that felt by HA is actually reinforcing the applied field. So in this case, since that local field is larger for HA and is reinforcing the applied field by more, you get a larger external magnetic or effective magnetic field for A than you do for B and C. B and C here are overlapping. They're very close in chemical shift, and because they're so close in chemical shift, the coupling constant is larger than the difference between the chemical shifts. So what we're seeing is HB, the green ones here, are split by hydrogen A with a large coupling constant, and then they're split by hydrogen C with a very small geminal coupling. The geminal coupling for sp2 hybridized hydrogens is very small, typically between 1 and 3 hertz. And then Hc is split by Ha with that fairly large coupling. It's actually identical to the difference between the 1 and 2 peaks here, because that's the AB coupling, and the AB coupling, the AC coupling is the same in both cases. And then the same geminal coupling, which is very small, so we see the same difference between these two peaks and between these two peaks. So that's a typical ABX pattern. It's a little messy here. This is recorded at 90 megahertz because the chemical shift difference is so small relative to the coupling constants. If we run that same spectrum, but we do it at 300 megahertz instead, you'll see now, because there are a larger number of hertz for each part per million, we have 300 hertz between each part per million, which means we have 30 hertz between our 4.8 and our 4.9, representing 0.1 part per million. Now the center of the peaks are far enough apart that the overlap is no longer there. So HB and HC in this case are distinctly different. Right? The coupling constants are the same, even at the higher field, because the coupling constant is a field-independent number, whereas the chemical shift, the number of hertz downfield from tetramethylsilane increases as the field strength increases. And then we divide through by the spectrometer frequency to give ourselves the same value. So this is 4.8 part per million on a 300 megahertz instrument, just as it was on a 90 megahertz instrument. But in terms of hertz, you're multiplying 4.8 by 300 here as opposed to by 90. It's possible to have ABX patterns on molecules that are not that do not have a double bond. And one example is asparagine, which is one of the 20 common amino acids. So in this case, you'll notice we have 2 hydrogens on our NH2 group of our amide, and 3 hydrogens on our ammonium group in the alpha position. Those 5 hydrogens are all exchangeable with water, and so they will show up in the same place as the water residual for HOD, and won't be they won't be visible in the actual spectrum because these will have been replaced by deuterium. So we'll actually only see 3 signals: the CH2 group, which we're labeling A and B, and then the hydrogen on the alpha position, right next to the carboxylic acid, which we will label gamma here, or I labeled it X. Here's a 3-dimensional structure, and you can see that this carbon-carbon bond, right, would allow some rotation, but the most stable conformer has the carboxylate group and the amide group opposite each other, so that we can maximize the cancellation of the dipoles between the 2 carbon-oxygen double bonds. And that means that these 2 hydrogens will not be in the same relative position with respect to the NH3 group. That's a little clearer if we look at a Newman projection. So looking at this Newman projection, we've arranged these carbonyl groups so their dipoles are going to cancel as much as possible. We don't have free rotation now because there's quite a bit of steric hindrance associated with putting this NH3 plus group, right, over the top of the carbonyl, right? So it's kind of locked in this conformer, which means that if you consider the alpha hydrogen, right, the hydrogen that's on this position next to the nitrogen, that one should be the furthest downfield because of the presence of both the nitrogen and a carbonyl group. This hydrogen should be in a different environment relative to one of these hydrogens relative to the other. We would expect to see a large coupling for the 180 degree dihedral angle, about 12 hertz. We would expect to see a smaller coupling for a 60 degree dihedral angle, a gauche relative orientation, and that's about 4 hertz. And then on an sp3 hybridized carbon, we see a very large geminal coupling, typically around 18 hertz or so, even larger than a trans coupling from the alkene. So if we look at the spectrum of asparagine, we have the HOD peak with the exchangeable hydrogens here for water. Hydrogen X, which is the hydrogen attached to the alpha position, is down here, and you'll see that we have a 4 hertz coupling, a small coupling between the first 2 peaks for hydrogen A, and then we have a larger coupling from hydrogen B, right, the 1 and 3 positions. If you look here, A and B are coupling to each other with a very large geminal coupling, and because they're splitting each other, they're leaning very heavily towards each other. These 4 peaks up here are actually a doublet of doublets, but there's a great deal of lean towards the hydrogen they're splitting, and these 4 peaks are one coupling, but there's also a great deal of lean towards each other. So we see the smaller coupling, right, that's the 60 degree dihedral angle, and then we see the large the 1,3 here, we see the large coupling for the geminal AB coupling. Here we see that same large AB coupling, so the distance between peaks 1 and 3 of this doublet of doublets and peaks 1 and 3 of this doublet of doublets should be the same, but then the difference between peaks 1 and 2 is the larger of these two couplings, which is the 180 degree dihedral between hydrogen B and hydrogen X. So this is a distinct ABX pattern. And in this case, since we're running this on a 300 megahertz instrument, this was actually run on our instrument in our NMR room, we have a large enough difference between the chemical shift in hydrogens A and B that they're not overlapping with each other. Alkynes are interesting because the CH peak on the alkyne, which is not as far downfield, because remember the alkyne orients itself parallel to the applied field rather than perpendicular. The hydrogen doesn't have any hydrogens on the adjacent carbon, yet it's still split into a triplet. That is a 1,3 coupling. That's a long-range coupling, and that's typically similar to the geminal coupling in an alkene at about 1 to 3 hertz. So we've got a triplet, but we've got a triplet with a very small coupling constant. The CH2 group here is now split by a CH2 adjacent to it into a triplet with a reasonably large coupling constant, probably around 7 hertz, and then each of those peaks of that triplet is split into a doublet with that small coupling. So we see a doublet of triplets with a small long-range 1,3 coupling and then the relatively large plain old alkyl coupling. The methyl triplet upfield is typical, or CH3 next to a CH2, and then the 2 hydrogen multiplet in here, that's split by 5 hydrogens. The pink and the blue hydrogens split the CH2 in the middle with approximately the same coupling constant. So even though those are magnetically distinct, the coupling constant's the same, and it follows Pascal's triangle, and we get a sextet for the 5 adjacent hydrogens. So small coupling constants like that for peaks in this range between about 2 and 3 are often indicative of an alkyne. On an aromatic ring, a pattern that you will learn to recognize is this pair of doublets leaning towards each other, each 2 hydrogens. That is very typical for a 1,4 substitution or para substitution on an aromatic ring. These 2 hydrogens are magnetically equivalent. These 2 hydrogens are magnetically equivalent, so they show up as 2 hydrogen peaks, and then this hydrogen is split by the one adjacent, this hydrogen is split by the one adjacent, and since there's symmetry, that coupling constant is identical. So we got a pair of doublets leaning towards each other, a total of 4 hydrogens in the aromatic region, typically a 1,4 pattern. Notice we have our aldehyde hydrogen here between 9 and 10. That's a singlet because there are no hydrogens on the adjacent carbon. And then we have 2 identical methyl groups attached to nitrogen, which puts them in the 3-ish range, 2.5 to 3.5 for hydrogens adjacent to nitrogen. By contrast, if you have a tri-substituted benzene, we now only have 3 hydrogens in the aromatic region, and they're all magnetically distinct. They show up in different locations. You'll notice that hydrogens, the green hydrogen here and the blue hydrogen, are splitting each other, even though they're not on adjacent hydrogens with a small coupling. That's another 1,3 coupling, a long-range coupling. And because the hydrogens are in a little bit of this W shape, an upside down W in this case, you generally see a 1,3 coupling when you have that W arrangement. And you'll see that actually on chair cyclohexanes as well. This hydrogen is split into a doublet of doublets. We've got a larger coupling because this hydrogen is actually adjacent versus a 1,3 coupling. And then we've got the smaller 1,3 coupling. And then the pink hydrogen is just split with an ordinary coupling constant. The distance between peak 1 and peak 3 of this doublet of doublets should be identical to the distance between these two, and the distance between peak 1 and 2 should be identical between the distance between these two. And we've got a 3 hydrogen singlet. Notice it's closer to 4 rather than 3 because in this case the methyl group is attached to an oxygen rather than being attached to nitrogen. Carbon NMR can be run in a couple of different ways. This is showing a fully coupled carbon NMR where we have not decoupled the hydrogen, and so the methyl group is showing up as a quartet and the CH2 group is showing up as a triplet. But then you also see the splitting from the hydrogens on the adjacent carbon. So each peak of this carbon quartet for the methyl group is split into a triplet by the CH2. Very small coupling for that secondary effect as opposed to the hydrogens directly attached to it. And each of these peaks from the blue one is split into a quartet by the 3 hydrogens on the methyl group. That makes things messy. You'll notice the signal to noise is not very good here. So typically what we do is we decouple. Right? You'll also notice that what's usually a singlet for the CH3 groups of the tetramethylcyanine is also split into a quartet here. So normally what we do is decouple so that all the hydrogens are in the beta state all the time. That's that wideband alternating phase low power technique for zero residual splitting, or waltz decoupling. And so the CH3 group is a single hydrogen, or single carbon, and it's showing up as a singlet. The hydrogens are not splitting it. We've got a tertiary, a CH group, right? So here it is. That's the single hydrogen. The CH2 groups adjacent here are showing up as one singlet because of their magnetical equivalence, and then these two black hydrogens show up as a slightly larger peak than this one because there's only one CH2 at the 4 position versus these two, right? You can't use the integration here very well because in general methyl groups are bigger than methylene groups, and methylene groups are bigger than methine groups. So we have both the nuclear Overhauser enhancement because of the adjacent hydrogens and the fact that there are 2 of these and only 1 of these, and we can't decouple those. This spectrum is here not because of the one on the top, that's just an aldehyde, and you'll notice it's showing that long-range coupling again. But what I want to illustrate here is what the carbon spectrum looks like for cyclohexanone. The quaternary carbon, the carbonyl group, is very small, and between 200 and 220, about 210 in this case. So it's a quaternary carbon, no nuclear Overhauser enhancement, so it's very small. We generally see the CdCl3 solvent. Deuterium splits this carbon into a triplet, so we have 3 peaks here centered at 77 of equal intensity. And then we have a single CH2 furthest from the carbonyl group, upfield, and then a pair of CH2s here and a pair of CH2s there. So there's symmetry. One of the things the carbon NMR allows you to determine is symmetry. We know this is a C6H10O molecule, but we only see 4 signals, and that tells us that there's going to be a plane of symmetry somewhere in the molecule. And then we talked a little bit about a DEPT, or distortionless enhancement by polarization transfer. Here's the spectrum for limonene, right, the entire spectrum. You'll see that the quaternary carbons, carbon 1 and carbon 8, are quite far downfield. You'll see that the other carbons that are attached to the double bond, right, the carbon 2 is downfield in that region where you expect to see alkenes between 100 and 150. Carbon 9 is also there. And then up here we have our methyl groups, carbon 7 and 10, which is the furthest upfield. And then we have our methylene groups, carbons 3, 5, and 6, kind of overlapping with each other. And then our methine peak, carbon 4, is the furthest downfield. So generally CH3 groups, and then CH2 groups, and then CH groups in that region between about 10 and 40 for just plain old alkyl peaks. This is showing a spectrum that shows just the methyl groups, and then we have a spectrum that shows just the methylene groups, and then we have a spectrum that shows just the methine groups. And we can do that by changing the pulse sequence, changing the way the instrument behaves. The attached proton test would leave these 4 peaks up because there are odd number hydrogens, and then it would flip these upside down. So you would see the methylene groups pointed down. But this is a full DEPT spectrum where we've got the full spectrum and then just methyl, just methylene, and just methine peaks. So the ABX pattern is something you should be prepared to recognize, and the difference in coupling constants between geminal hydrogens on an sp3 versus geminal hydrogens on an sp2, long-range couplings, a 1,3 coupling that you see across an aromatic group, or that you see across an alkyne, those are relevant. And then the different couplings for cis and trans on the alkene are also things that you should understand.